All right, hello class. Today we're going to start the 4.4 applications where we're going to have limited growth, right? Which means unlike the last ones where we had uninhibited, our function technically grew forever as time went by and got faster and faster, grew exponentially. These equations, which are called logistics equations, are cases where we can't grow indefinitely. We've got limited growth. All right, and again, a lot of applications actually fall because a lot of populations grow exponentially. And so there are lots of applications that involve logistics equations. All right, so that's what we're going to talk about in this set of notes. We're going to kind of set it up and talk about all the important aspects. And there's a lot. There's a lot going on in these types of curves. And then the next set of notes, or the next lecture, we'll talk about, or we'll do applications. All right, so after we kind of set it up and explain what logistics curves are. All right, like I said, there are lots of applications. A lot of things tend to grow on a logistics curve. All right, so first the domain, range, and then graph and properties. All right, so our equation is some population or quantity, where C is just a number. It's an important number, and I'll talk about it when I get it set up, over 1 plus AE raised to the K times sign. K still represents a constant, a growth constant. It still has to do with how fast or slow the logistics curve is moving, and again, stuff like that. So again, it's still important. Alright, so A is just a real number value, and T represents time. So the domain first. Alright, domain is time. Days, months, hours, minutes, seconds. And time can only be positive. So our domain is always 0 to infinity, right, because of time. Range has to do with the application. And actually, it comes from the parts of the equation. All right, range are the outputs, right? The y values. And so the range, well, we start with whatever the initial population is, which that would be, again, now the initial population is not part of the problem. I have to find it. I have to plug 0 into this equation, 0 for time. And whatever that value comes in, that's where my population is starting. That's where my logistics curve is starting. All right, and then again, it doesn't grow forever. All right, it's not shooting off to infinity like our other examples. What's happening here is it's actually going to approach, like I said, that C value is important. That's what it's approaching. All right, so C would represent a number. All right, it'd be like 1,000 or 10 or whatever. When we get to applications, we'll have it. But my range is my starting value up to that C value. So plug 0 in to find my starting population, and then my function approaches C. Technically, it never equals C, but it does approach C, and we'll talk about it. It actually has to do with a limit. All right, so again, we'll talk about that once I get the graph. So now the graph and sort of the properties. All right, so the graph, we only graph on the first quadrant. All right, so a logistics curve, my x-axis really is my t-axis. That's time, and that would represent whatever time period it's growing over, days, months, weeks, hours, seconds, whatever. Only in the first quadrant, 0, right? Time starts at 0, population starts at time 0. All right, then we mark off y equals c. That c value is important, and it's going to be an asymptote. All right, again, that's the c that's up here in the numerator of my logistics curve. And I'm going to draw it as a dotted line because it is an asymptote, and usually we draw asymptotes as a dotted line. All right, so this would be the line y equals c. This is a horizontal asymptote. Alright, so our population, we'd plug 0 in to our population equation, our logistics equation, and so we'd start at whatever that amount is, population at 0. And then the behavior of the logistics curve. Alright, the logistics curve initially starts out growing fast, kind of exponential growth. It goes up and grows fast. Alright, then it reaches a point where it's going to, and again, I'll talk about that point in a second. So this would be growing really fast here. All right, this first piece of the logistics curve. All right, then it reaches a moment where it's growing the fastest, and then it switches, and it's still growing, but it's going to grow at slower and slower rates as it approaches that horizontal asymptote. So as time goes by, it's going to approach that asymptote. All right. Oops, didn't mean to erase that. This point where it switches, well, it's, if you can look at this, it's concave up on this piece and it's concave down on that piece. And so that moment here is an important moment. It's an inflection point. and we're going to probably want to find it when we get to applications. It actually occurs in all of these logistics problems we're going to do, at 1/2 whatever that c value is. Alright, so again, that would be the function value, the y value. So whatever 1/2 that c value is, which c value comes from the numerator, that's what my inflection point is. Alright, so again, it'd be occur at some time. Alright, my inflection point would occur at some value t, which often we'll have to find. Alright, that would be some t for my inflection point. And it's important. Alright, first of all, it's where it's switching concavity, right? I'm concave up. At this moment, I switch to concave down. Alright, and remember what that means. Concave up means I'm increasing at faster and faster rates. My slopes are getting bigger, right? I'm increasing my population at faster and faster rates. Right? My slopes are getting bigger. That's what it means by faster and faster rates. My slopes are getting, so my population's increasing, and it's increasing faster. It's exponentially increasing on that piece. That piece would represent sort of a piece of an exponential function there. And then at this moment, it switches. Now that moment's important because it's switching. It happens at 1/2 c, and we'll talk about what c is in a little bit. But at this moment where it's switching, I have my biggest rate of change. This is when I have my biggest rate of growth. Alright, so whatever this is, if this is population, this is when population's growing the fastest. Alright, this is its biggest slope. Steepest moment on my curve. Alright, then after that moment, it's concave down. So after that moment, I'm still increasing, right? I'm still moving up, but at slower and slower rates until eventually it basically levels off. Alright, once a long time passes, and it doesn't necessarily have to be a long time. Again, if the k value is fairly big, it'll approach this fast. If it's small, it'll approach it slow. But it basically approaches slower and slower rates, and it flattens out to horizontal, and the rates are so small that we call it 0. Alright, it rounds to 0. And so eventually we're going to get a 0 slope, 0 rate of change, where we don't consider the population growing at all, right, or this quantity growing at all. Alright, so the derivative will eventually level off. It will zero out after time. Rate of change is nothing as time passes, as time goes by. Alright, and so that's sort of behavior of the function if you think about it in terms of its limit. Or not limit, we'll get to a limit. As terms of its rate of change, its derivative. Alright, so the derivative would be positive here, right? It's positive. Actually, the derivative is positive everywhere. So we'd have a positive derivative, but it'd be increasing. So here we'd get a positive derivative, concave up, which means my second derivative would be positive. Alright, inflection point where my second derivative equals 0. And then I'd still have positive slope, so first derivative still positive on the concave down piece, but now my second derivative is negative because it's concave down. So again, the inflection point is when my second derivative is 0 in this case. Biggest rate of change, biggest slope. Slope's not 0. Slope's really big at that moment, right? Biggest on the entire curve. Alright, so here my derivative would be bigger than 0. My second derivative is also bigger than 0. Here, my first derivative is still positive slope, still increasing. But now the acceleration, alright, I am negative slope, or negative rate of change, not slope, negative acceleration. I'm decelerating, I'm slowing down. Till eventually it does zero out. We consider it zeroing out. After a long period of time, it zeroes out. Alright, so that's what properties if we're talking about derivatives. Alright, now I'm just going to talk about properties of the function in general. We're going to talk about that c value. That c value is very important. And it's in my function. Alright, so that horizontal asymptote. Alright, so again, this is my general logistics curve. And so we've got this c value, which again shows up in my domain of my logistics function. And what that is that c value, right, is what we call the maximum capacity. So that horizontal asymptote, y equals c, which again is a horizontal asymptote, is what we call the maximum capacity of the population, or the quantity. As time goes by, all right, it goes to infinity, all right, as I'm moving off to infinity in time, the population function approaches that c value, and eventually it gets so close, arbitrarily close to that c value, that we say it's equal to that c value, or the limiting value is that c value. And so this again is a limit, right? This is a special type of limit to infinity. All right, the limit as time goes to infinity of our logistics curve equals c. All right, that's the limiting value. As time goes by, the population will approach c, and eventually it gets so close to c, arbitrarily close to c, as close as anybody could ask me to get, that we call it c. C will be where it'll max out. Right? It's its limiting value at c. All right, so its rate of change approaches 0 as time goes by, and its maximum capacity approaches c. All right, this moment here, right, the inflection point. All right, I'm going to talk about the inflection point. All right, the inflection point occurs at half capacity. Right, at 1/2 whatever that capacity is, right, that would be the function value, the y value. We'd have to find the time, right, when that occurs. But that's important. The inflection point is when our function switches from concave up to concave down, increasing really fast, to, we're still increasing, but we're slowing down, and eventually we're going to taper off until it again has a 0 rate of change, all right? And so that's when the inflection point occurs. So again, we'd have to find time. When does that time happen? At that moment. And so there's two ways to do it. You can either take your function, set it equal to that half capacity, and solve for t. Or there's a graphing method, and when we get to the applications in the next set of notes, I'll show you the graphing method, all right? And that would be, again, when we get into the next set, the logistics solving equations. All right, so just some summary, some important points. So I'm going to write down sort of summary about the logistics curve. All right, so again, only graph it in the positive, right, in the first quadrant. All right, time is only positive. All right, in the long run, all right, as time goes to infinity, and we'll look at this in applications. We'll actually plug in numbers to kind of see how this works. So as my t value goes to infinity, the population goes to whatever that c value is. So again, my function approaches that c value in the long run. All right, and that's not the only thing that happens. All right, so the population goes to c. All right, and then what happens in terms of the derivative? All right, the derivative, the rate of change, right, slopes, go to 0. All right, my derivative function will approach 0 in the long run. All right, as time goes to infinity, my population approaches this c value, right? My function approaches the c value, and my speed, my rate of change, tapers off and flattens out to 0. And so that's what's sort of important about the logistics curve. My limiting function value is c. My rate of change has a limiting value of 0. It approaches 0 as time goes on. Right? So again, this is sort of what's happening in the long run after many, many, many time periods pass. All right, then the inflection points so then the other aspect is the inflection point. So at half capacity. All right, so the second or last sort of note about this And then next video will be about applying this, looking at applications of these. All right, so the last sort of, again, important thing to take away, important property. All right, the inflection point is at 1/2 capacity, 1/2 C, and it's when the rate of growth is the fastest. Right, it's when the population speed is the fastest, biggest slope. All right. So again, right after that, we're going to switch. So before that, we were concave up, which means we were moving fast. All right, we were increasing. The speed was increasing. It'd be like hitting your accelerator, and your speed's going up. And then you're going the fastest at that moment, at the inflection point, and then you switch to concave down. All right, so you peak out at your speed peaks out at the inflection point, and then so you're hitting your accelerator, increasing faster and faster and faster. Your speed's going up and up and up and up, until you hit the inflection point, right? And then that moment you switch to decelerating. So it's kind of like you either let go of the gas pedal and you start to slow down. It's probably better more than hitting the brake. So you release the gas, and now your speed's going to slow down, slow down, slow down, slow down, slow down. And so you're slowing down until eventually you stop. All right, rate of change stops. And so that's sort of the best way to sort of think about it. Your speed is increasing really fast, so you're hitting your accelerator over the first half of the capacity, so you're moving up. So this would be your speed would be moving up fast. Then at this moment, you're the fastest. This is when you hit your maximum speed. And then you release the gas pedal. After that, your speed starts to slow down, slow down, slow down, until eventually, after time passes, you get to 0. Right? Your speed is you're no longer moving. You've slowed down to 0. All right, and so that's sort of how logistics codes work. All right, so we'll stop there. The next video will be on applications of those.